as much as we needed to get the credits, but we were kind of curious about what happens when we look at the rest of the building. Isn't there a lot of this carbon story that we're not looking at? And so we started thinking about where there might be gaps in our system. And so we decided to take a look at it. Uh, we looked at basically all these different sections of the building, had to mix together a whole bunch of different studies. We used Tally for basically anything architectural, structure, enclosure, interiors. That doesn't include the furniture or any of the real kind of built-in millwork or anything. But it includes all of the interior partitions as well as any sort of interior curtain walls or anything like that, any sort of interior finishes that are ornamental in nature. We looked at the landscape using the Climate Positive Design Pathfinder tool. It's one that if you all aren't using on your projects, you should. It's a great one because it's, when we're looking at all the carbon studies, it's the one that always gives you a negative number, or generally gives you a negative number, which is a really fun thing to see. Operational energy use, just typical energy model. And then the MEP equipment and refrigerants, these came from 2 different studies. We don't have a tool right now to actually study these things flat out. So the MEP equipment numbers come from a Carbon Leadership Forum study, and the refrigerants come from a PAE study that was performed earlier this year. When we start layering these things in, it really kind of fleshes out this graph a bit further than those 2 lines that we normally see. And what this allows us to do is that we can start taking slices through the data and realize what the total carbon in the system is at any given point in time. As we all know, right off the bat, the structure, enclosure, and the interiors are all big players right at the beginning. But as you start moving forward and you're looking at operational energy use and say interior refresh of interior materials and refresh of systems, and also the amount of carbon that the landscape is sequestering, all of these start to play into the overall story. And in the 100-year lifespan of the building, there's a lot to look at. Basically, when we're looking at the LEED whole building LCA, we're only looking at about 33% of the total carbon on this project. And to be honest, we're probably, there's probably even more unexplored carbon when we start really looking into the furniture and finishes that weren't included in the interior study. But this brought us to another, thought of how much can we trust these extrapolations into the future, and where do we draw the line on what we think is actually the correct amount of, where do you think that this information kind of falls off from being useful as a guide? And so to look at this, we started thinking about into the future. 2045, as I mentioned, Washington State's grid is going to decarbonize. So at about that point and up to the years up to that, we're going to see a tapering off of the operational energy use carbon. And hopefully it just goes to 0 around 2045. When we look at the landscape, our tool, gives us an output for about 50 years, and we're extrapolating it to the 100 years. But to be honest, the landscape will eventually reach kind of a stasis point with carbon. As those plants mature, they generally reach an equilibrium where they're no longer sequestering as much carbon as they did in their early stages. When we look at interiors, the data there is coming from Tally's model, where you have refresh rates for each one of the materials. The thing is that some of these refresh rates probably aren't actually representative of how the building will exist in the future. We can tweak these, but there's a lot of unknowns because as the building grows and ages, it's really up to the client as to how they refinish these areas. And if they're choosing high carbon materials or low carbon materials and low carbon furniture and fixtures, things like that. And it's our belief that over time, hopefully as the grid becomes cleaner and as we start moving to more of a carbon-free society, hopefully we'll be on the low end of the scale, but over time, the variability increases. And then finally, when we're looking at the studies that we're using, say like the MEP system one, and this is looking at all of the different mechanical equipment, as well as the ductwork and electrical wiring and piping, plumbing, things like that are in the building. The study that we were looking at had really tight revision cycles of about 15 years. And our belief is that this was more for sort of a core and shell office building where you might have tenants coming in and replacing these things over time. But for the school building, we don't really think that that's going to be the case with this building. So we're hoping that this is something that is actually a conservative estimate, and that the real answer is going to be far less. So the question is, what does this mean, and how do we actually use this looking at our projects now? And the way that we're looking at it is that we have some, strong certainties and strong uncertainties. We know that the structure is going to be something that's really dialed in. This is something that is just paid off for right when you build the building. All of that embodied carbon is going to be in there and going to be with the project for the rest of its time. The operational energy use, because we've been doing a lot of operational energy use studies, we feel pretty good about, even with the proposed changes in the future. We have a pretty good feeling that that's going to be a conservative estimate. And so best case scenario, we're better than we think we were. But the enclosure interiors, as I mentioned, those are both things that are going to really kind of depend on how we maintain and update this building. And then the refrigerant and MEP and landscape, these are things that we kind of don't feel as comfortable about. We need different tools. We need to really work on these tools. And we just need more studies to understand what we're looking at. And this kind of brings us to the last part of just looking at this case study and talking about how LMN ends up using a lot of this data. This graph is, all the solid lines are actual data coming out of Tally, as well as the energy model. And then the air bands on the tops of each one of these are more gut feeling. And how I'd explain is that stage A1 through A3, these are stages that we feel pretty good about because we have EPD data that we can take it from. We know that this is stuff that is relatively well measured carbon. But as we move into, say, the B stages of use and replacement, and into the C stages of end of life, these are areas that really require us to extrapolate our feelings on the future, and the numbers that are associated with them really kind of correlate with those beliefs and the theories that we have on how the building will actually age. So they're described as a single number coming out of Tally, but when we look at it in reality, there's going to be a range. There's going to be, say, the what we hope the heavy timber materials for the structure won't actually be thrown into a landfill. They'll be reused in some way, shape, or form. But with Tally, you just kind of get a blend between either that material being burned for biomass energy, being thrown into a landfill, or eventually, or potentially reused. And you get sort of the average of those numbers, depending on what the national average is. So to reiterate how LMN ends up using this is that we tend to look at the A stages more closely with our project, because these are things that are bought into right off the bat. These are things that we know that when we build the project, these are debts that we're going to incur, and the lower that we can get these right off the bat, hopefully the better the future stages will be. So that's the real quick version of what was presented there. So let me stop sharing that. Do you have any questions? Yeah, so I'll have to share that link. Someone's asking about sharing a link for the PA study, and I'll get that out hopefully later in this meeting. Alex, you want to take it away on yours? It doesn't seem like I'm getting any questions on this.
Well, actually, before then, I have like a ton of questions, but hopefully I can sneak one of them in. So when you're talking about quantifying the uncertainty, how do you kind of set the upper and lower bound of those box and whisker plots when you think about how much room there is for the total result to change based on, say, different replacement rates?
So let me pull that one back up again real quick. Just as a heads up, if you're going to ask a question, I can't see the chat when I'm sharing my screen. So if you're not asking it on mic, if someone could ask it for you, that'd be great.
I can take care of that.
So with the upper and lower bounds here, these are rough. The upper and lower bounds on the A1 through A3 were set based off of what we have coming out of EC3. Mm-hmm. And those are going with generally that 25% air band that you get on EC3 on a lot of categories. The enclosure, if you look at the way that Tally outputs its data, basically each material has a single A1 through A3 stage and the C2 to C4 stage. And then for the B stages, it just multiplies it by the amount of times that that material is going to be replaced over the lifespan of the building. So the more replacement, the more that airband could potentially grow, but also I would argue that basically the more replacement cycles, we're just kind of giving it a judgment value and expanding that out as we move into the future, because each time you replace it, we're not positive how you're going to necessarily replace or maintain this. And hopefully, as mentioned, our options get better as we move to the future.
Awesome. Well, this is a really, really interesting study because I feel like in embodied carbon modeling, we always get kind of discouraged by how uncertain the data can be and not sure what is exactly around the corner that we're not accounting for. So to at least have a list and a first take at how much that uncertainty could represent in the overall life cycle of a building is, I think, very valuable. So one more question, in terms of next steps, so will you be using these findings to kind of apply uncertainty factors to your early models? Or is it more case by case?
We'd like to, but I think right now it's going to be on a case-by-case basis. I think it's something that we're just starting to look at. And we're just now figuring out ways of really kind of digging into the tally data to start tweaking out some of the items that we really want to look at. So this is something that I'm excited to see, you know, as our library of carbon models increases. I'd really like to see this applied to all of our firm's models and just see where we end up. But right now it is pretty, this is just the first take.
Oh, that's awesome.
So we have a question in the chat about biogenic carbon and how Tally incorporates that.
You know, that is actually one that I haven't had a chance to dive into the numbers on. When we were looking at this one, we realized that the biogenic numbers coming out were a little scattershot. So we ended up deciding to exclude them for this because we feel that for this study, just looking at the total carbon story of this, going with a more conservative metric would probably be an easier thing to look at and also get rid of those boundary issues that sometimes exist when you're looking at biogenic carbon. As
I remember digging
more, I'd love to find out how exactly it's tallied in there, but to be honest, right now I don't know.